network layers and devices operations. In this course, we will focus on communication models, so-called layers. You will learn how different protocols fit to different communication layers. You will also understand the network devices types and how they operate in relation to communication model. As you remember from bits, frames and packets course, we might already see some relation between information structure that we can call layers of communication. We remember that bits are serialized by interface and sent to medium link as physical voltage levels, pulsing light, or electromagnetic frequency change. We know that those bits are interpreted by devices and form the frames, and in turn the frames are strictly related to medium type like copper cable or wireless access. We also know that frames encapsulate the packets that are transported from the source to the destination. In other words, end to end. All this makes some logic similar to layers. You can think of layers like a tall building. Each floor is a layer. For human, only the highest floor is visible, but for devices all layers are important. Imagine yourself looking at the tall building. Mike, who is on the left, writes hello message to Alice in application like for example Skype. Application needs to know that to send message, it has to portion the message to chunks of data called segments and then pack them into packets. In turn, computer sends the packets via network interface like wired Ethernet cable. So as we know from latest course, interface encapsulates the packet with frame and serialize the bits as physical impulses on the wire. On the receiving side, the logic is opposite. Bits from the wire are interpreted by network interface card, and thanks to frame fields and packet is decapsulated and forwarded up to application layer, meaning for example Skype. And Alice sees human readable hello from Mike. Let's stick with layer model for a while. Different communication protocols operate at different defined communication layers. Protocols are the suite of common methods signaling messages that can be understood and agreed between the parties. Each protocol is strictly related to particular communication layer. For example, every application like Skype or browser traffic understands common suite of messaging to transfer the data. So for application layer, HTTP is the most common protocol in the internet, and for endpoint application, this transfer is done directly with HTTP messaging. To send human-readable text to the receiving party, first, application needs to instruct communication stack to segment the message. These segments are controlled by Transmission Control Protocol, TCP protocol. It is in transport layer 4. There are two common layer 4 protocols, TCP and UDP. Transmission Control Protocol is used with application that needs data delivery assurance. This includes, for example, browsing or file transfer, when the acknowledgements are needed. Common application layer protocol that use TCP as transport are Hypertext Transfer Protocol (HTTP), File Transfer Protocol (FTP), or Secure Shell Protocol (SSH). Communication in TCP assumes acknowledging each delivered segment by the receiver. However, if segment is not acknowledged by receiver, it is resent by sender. Always before TCP starts to communicate, it starts with parameters negotiations. Parameters includes maximum segment size synchronization between parties. This mechanism uses 3 messages and is called three-way handshake. These messages are TCP SYN, like let's synchronize, SYN ACK, like acknowledge, and ACK from the sender, like acknowledge to. User Datagram Protocol or UDP is used with applications that need no delays, but datagram drops are accepted. This includes real-time apps like video or voice streaming. Common protocols that use UDP is Real-Time Protocol, used for voice over IP communication, or IP telephony. UDP datagrams are sent one after the other without acknowledgements. During communication in transport layer, the most important information is on which port number a particular application listens for an information. This is common for both TCP and UDP protocols. Port numbers are used on both sides, sender and receiver. To make connection possible, sender sends the TCP segment sourcing it from particular port and uses destination port of the receiver. Of course, as we already know, to get to the receiver, sender needs to know also IP address of this receiver. But IP is the subject of network layer. TCP segments or UDP datagrams are encapsulated with IP packet. IP packets operate at network layer, layer 3. As you may remember, IP packets provide IP addresses information in IP headers. That is why primary information for layer 3 is IP address. Because transport protocols use port information and packets use IP addresses. We have now 4 parameters describing connection: source IP, destination IP, source port, and destination port. So on particular host taking part in communication, there is one port and one IP address open for each session. Combination of layer 4 port and layer 3 IP address is called socket. You can see on the picture the socket of 192.168.110.2000 on host A and 192.168.120.AT on host B. These two sockets describe complete TCP IP connection. After having TCP segment or UDP datagram encapsulated with IP packet, computer needs to send this information out of particular interface. If this is Ethernet interface, network interface card is used to encapsulate IP packet with frame to forward it. Sender injects physical address of NIC, called MAC address, as source and physical address of receiver's NIC as a destination MAC address into the frame header. The prepared frame is then serialized and put on the wire as raw voltage levels. What you have learned is that there are layers of communication in networking. If application needs to send data to other party system, it uses application layer protocol, for example HTTP, to organize data. And then application layer sends the data to transport layer, layer 4, to segment data and ensure data delivery when needed. Transport segments or datagrams are handled by layer 3 IP packets that treat transport segments as IP payload. When operating system decides which interface to use to send the packet and chooses Ethernet NIC, the adapter encapsulates the packet with Ethernet frame in data link layer and then sends it to physical layer for serialization. The opposite process is done on the receiving side. Physical impulses are interpreted by NIC in the physical layer. Then, adapter assembles the frame with a payload in layer 2, decapsulates the packet and sends to upper layer 3. If packet is interpreted, IP header is removed and transport layer is informed to analyze the transport segments or datagrams. After segments are recognized and assembled, they are sent to application layer to present it on application level. Application presents the data to user. Historically, in mid-1990s, there was an OSI model, but today vendor agrees to common TCP IP model consists of 5 layers. Those layers are application, transport, network, data link, and physical. When you have understanding about network layers and dependencies between them, now it's a good time to become familiar with network device types because they perfectly reflect network layers model, especially in lower 3 layers. The most common network device operates on particular TCP IP layer. First one is a hub. This is old one and not commonly used nowadays. Hubs use signal multiplication. In other words, when electrical signal representing bits arrives on one hub port, this signal is copied and transmitted to all other ports except one was arrived on. So this is pure layer 1 communication because device operates on electrical signal purely. Hub doesn't understand nor frames neither packets. This of course causes unnecessary traffic and signal collisions when devices transmit simultaneously. Things dramatically change for Ethernet switch operations. Ethernet switch understands Ethernet frames, so operates at communication layer 2. Switch, unlike hub, analyzes destination MAC address included in frame header. and forwards the frame according to MAC and switch port binding. Important thing is that switch doesn't produce unnecessary traffic like hub does. This process is called switching. Switch learns and stores MAC and physical port bindings in piece of memory called CAM or TCAM. Classic layer 2 switches doesn't look into IP information at all, like router does. Router is another commonly used network device type. Routers play a very important role as in small home networks as well as internet service provider network. They operate at network layer 3. Communication is based on IP header information. So for router, the knowledge where needs to route is crucial. Router has piece of memory called routing table, where stores all destination addresses and networks. Thanks to routing table, forwarding across internet and private network is possible. When Ethernet frame arrives at router's interface, router decapsulates packet, stripping frame and examining destination IP address from IP header. After proper destination is found, router forwards the packet via proper interface, encapsulating packet into new Ethernet frame and sends it out. To sum up, let's stick at the scenario when switch and router is on the way in relation to communication layer. Assume that computer A sends the information to computer B located in another IP network. Know that router divides and segments network to many IP network like layer 3 device does. Packet sent from A is encapsulated with an Ethernet frame and sends in the computer B direction. When frame arrives at switch port, switch looks into frame header, checking destination MAC of frame, which is router interface MAC. After finding outgoing switch port, it sends the frame, unchanged, out the correct port. This is layer 2 operation on frame. Frame coming on the router is stripped and the router looks into IP header where destination of computer B is written. After consulting routing table, which is layer 3 operation purely, router knows that computer B IP address is accessible via the right interface and encapsulates packet with new Ethernet frame. This time MAC address is one of computer B in frame header. Frame arrives to computer B and is decapsulated according to TCP IP stack. So what have you learned in this course? You are familiar with TCP IP communication model. You are familiar with network layers. You can recognize and differentiate UDP protocol from the TCP protocol. You know what is encapsulation and how does the decapsulation flow work. You know the network devices types and their operations. To learn more, watch the next video called Network Connection and Medium Types. To learn the basics, start with bits, frames and packets. Phil. Thanks for watching.